Hello guys, so welcome back to our lecture 11. This is second recording, and we're gonna explore another, example, another combinational circuit design. Okay, and this is one is really important, very important one. Okay, any processor has this guy, which is really, half adder, a circuit that adds or sum two bits, only two bits together. Also, it's really very simple design. Also, it will be our, a major step, a major foundation, a major base in which we're gonna implement more and very complex design, in the next videos. Okay, so let's consider it as a problem. So design a digital circuit that sum two bits together. Like for example, 0 and 1, it will be 1, and so on. Okay, so the first step is the truth table. Okay, so basically you have two bits, two inputs, and let's assume that we don't know the output yet. Okay, so 0 and 0, the sum of these two bits, the sum of 0 and 0 is actually 0. So this is the sum, 0. Then the sum of 0 and 1 will give you 1. Basically 0 and 1 is 1. Then the sum of 1 and 0 is also 1. Again, 1 and 0 is also 1. And now the sum of 1 of 1. Let's do this, in another. So away here. 1 and 1. This is basically 2. What is 2? 2 is 0, and we have a carry of 1. So look at this. This is 2 in binary, right? This is 2 to the power of 0, then plus 2 to the power of 1. This is multiplied by 0, so it will go away. Then you will reach 2 here. Okay, so 1 and 1 needs 2 bits. The 0 bit here, we're gonna call it same sum, but this second bit here, we call it a carry, because 1 and 1 is basically 0, and we have a carry of 1. Then 1 and nothing means 0, will give you a 1. So we need another column here, another bit for the output called the carry bit, and this is basically the sum bit. Okay, but remember, this carry bit, we don't have a carry when we added 0 and 0. So this was 0 basically. And of course, 0 is equal to 0, when we added 0 and 1, again, the carry was 0. And again, 0, 1 is just equal to 1. And when we added 1 and 0, again, this is similar to 0 and 1. Again, the carry is 0, and the carry will be only 1 at the last combination 1 and 1. So we need two outputs. Again, this is the importance, one of the important thing about truth table. It will give you an idea about so basically from the problem you can know how many inputs. We have basically 2 inputs because we want to sum 2 bits. But you may not have an idea about how many output bits you need. So we need now to design 2 functions, one called the sum, another called the carry. So we need 2 Karnaugh maps. Let's start by the carry. So 0, 0, then 0, 1. Just 1 here. So just you have one prime implicant, one essential prime implicant. So this is basically look x and y. So C is equal to x and y. Very simple. Actually, you don't need to make a Karnaugh map here because it's really very clear here. 3 zeros. Whenever an input is 0, the output is 0, and whenever the 2 inputs are 1, you have it's an AND gate. How about the sum? The sum is 0, 1, then 1, 0. Okay, so I'm sorry, this is 0. So 0, 1, then 1, 0, 1, 0. So you cannot combine these 2 ones, so you have 2 essential prime implicants here. This guy is x bar y, and this guy is xy bar. So the sum is x bar y plus xy bar. And what is this? This is basically the XOR. Okay, so the third step now is to implement this. So this is our half adder now. This is the box that we will call half adder from now on. We will not draw again the inside or the internal structure of the half adder. It is just a box like this. And do you know that there is an AND gate, okay, that have an X and Y, and there is a sum bit which is X, X or Y. Or you can implement it also using, we have for the XOR, we have a symbol for it, because basically we can do the XOR using one circuit. So you can, make design a circuit using transistors and so on. So to make XOR circuit, you don't need to do two AND gates and one OR gate. Although both are acceptable, because basically some technologies only allows you to use AND and OR. So at that point, we will not have, a dedicated circuit for XOR. So both are okay. This is half adder, and this is also, the half adder. It's basically the same. Okay, guys. Now let's, before we go forward, to our, next basically topic, let's explore one disadvantage of this circuit. So let's do, normal addition, something like 1, 1 plus 1, 1, which is 3 plus 3, which is 6. Okay, make it like this. So in here, let's add these together. Okay, just like, our chapter 1. So 1 plus 1, these are 2 bits. So we can here do, half adder. 1 plus 1 is 0, and we have a carry of 1. And now, before we continue, let's look at this. So here you will add 3 bits together. So you're gonna add the carry to this guy, then the result will be carried or added to this guy. It's the last one here. So this can be easily done using a half adder. But this is, there is still a question here. Okay? Because this is 3-bit addition. Half adder is 2-bit addition. Okay? So that's basically, an introduction for our next, circuit. Our next circuit is called full adder. Okay, which is basically can be summarized in the following sentence: design a circuit that add 3 bits together. Okay, this is full adder. And once we do that, implementation or that design, we're gonna relate the full adder to half adder, because basically, let's look at the example again. So 1 and 1, you're gonna add these two first, then the result will be added to that guy, right? So again, you have 2 half adders. So the full adder that we're gonna explore next is basically 2 half adders. Can be, plus some, we can say some overhead, we can say. Okay, so in principle, the full adders that we're gonna explain in the next video can be designed from scratch. Okay, and also can be designed using the half adder that we just designed. And this is the hierarchical approach. Okay, so this is basically, the first time that we're gonna see the how the hierarchical approach are really useful. Okay, thank you very much, guys, for watching this video, and see you in the next video. Bye-bye.